Okay, so let's unpack this. What if I told you the fundamental math describing a tiny subatomic particle, its whole weird existence, is actually echoed in how artificial intelligence
That's
reasons?
pretty wild, doesn't it? That connection.
Totally wild. And that's exactly what we're diving into today. This thing called the inner product. It's a mathematical tool, a really powerful one that helps us grasp both, quantum mechanics and how these big AI language models understand meaning.
hmm Semantic landscapes, as they call them.
Right. So our mission really is to figure out why this specific math is so vital for quantum probabilities, down at that subatomic level. And then how a related, maybe simpler version is driving AI.
Highlighting the overlaps, but also the really crucial differences, because they aren't the same thing at all.
Exactly. Okay, so here's where it gets, I think, really interesting. Quantum mechanics. We always hear about the wave function, psi, right?
The core concept.
But it's not like a wave in water. It's a complex probability amplitude. You said a plus I. So it has a size, a magnitude, but also a phase. My first thought is just, why? Why make it complex?
Well, yeah, that's the key question.
What?
And what's fascinating is that complexity, that I part, the phase, isn't just math for math's sake. It's actually how quantum particles can, well, be in multiple states at once.
Superposition.
Superposition, exactly.
Yeah.
And how they interfere with themselves, kind of like waves canceling out or adding up.
Yeah.
Now, to get a real probability out of this complex thing, something we can actually measure, a number between 0 and 1.
Need a specific step.
You need psi. That little star means you take the complex conjugate, so AIB times plus I.
Conjugate. I remember that from math class.
And when you multiply those, you always get A2 plus B2, a real positive number. That's the Born rule.
Okay.
Without that conjugate step, you just have a complex number, which, what does that even mean as a probability? It's physically meaningless.
So that psi guarantees a real probability, ensures everything adds up to 1, and explains things like interference patterns, like in the double slit experiment.
Precisely. It elegantly ties it all together.
Okay, complex numbers doing their magic for quantum probabilities. Got it. Yeah. Let's switch gears. Let's jump over to AI's world, the semantic space.
Right. Large language models, the LLMs everyone's talking about.
They start with text, break it into pieces, tokens, and then map these tokens to vectors, right?
Yeah.
But these are different. They're real valued vectors, high dimensional, but real numbers.
Exactly. No complex numbers here. Think of it like creating a huge map, a conceptual space where closeness means similar meaning.
So the vector for dog would be near cat, but like way far from car or philosophy.
You got it. That's the idea of semantic space.
So what does this mean for how the AI actually thinks? How does it use its version of an inner product?
It uses the dot product. You might see it written as Q.K.COA. This is basically AI's inner product for these real vectors.
Q and K, query and key, from the attention mechanism.
Exactly right. It's absolutely central to how transformer models work, especially their self-attention.
Yeah.
You take a query vector from one word, or token, and you calculate its dot product with key vectors from other tokens.
And that tells the AI how relevant they are to each other?
Basically, yes. Relevance, compatibility. It's how the model decides which other parts of the text to pay attention to when processing a specific word. It weights the importance dynamically.
But crucially, unlike the quantum rule, this isn't a fundamental law, is it?
Not at all. That's a key difference. These dot product values, these attention scores, they're learned heuristics. The AI figures them out by crunching massive amounts of data during training. They're optimized, not axiomatic.
Wow. So it's incredible. The same core mathematical idea, the inner product, showing up in these vastly different domains. One describing reality, the other meaning.
Yeah, if you step back and look at the bigger picture, both ISI and quantum and Q.K in AI are types of inner products, mathematically speaking. Both take vectors and map them to a single number, a scalar. And both concepts help define vector length, the norm, and also orthogonality, when vectors are totally unrelated, pointing in perpendicular directions in their space.
But the differences are profound.
Absolutely critical differences. First, the numbers. Quantum needs complex numbers for phase and interference. AI uses real numbers.
Right. No phase in the AI embeddings.
None. Second, the purpose. Quantum size is introspective. It's about the state itself, its own probability. AI's Q.K is interactive. It's about comparing different things, different tokens.
One looking inward, one looking outward, sort of.
That's a good way to put it. And maybe most importantly, the interpretation. Quantum results come from fundamental physical laws, the Born rule. AI results emerge from training data. their learned patterns, heuristics.
So it's a really deep mathematical analogy showing how flexible linear algebra is, but it's definitely not saying AI is quantum or vice versa.
Exactly. It's not a physical equivalence. One math describes physical reality's fabric. The other describes the fabric of, well, human meaning as captured in language.
So we've seen how this one elegant mathematical idea, the inner product, pops up modeling the quantum dance of particles and the complex web of meaning and language. It's pretty amazing.
It really is. And,
Yeah.
it raises this interesting question for you to think about.
Oh.
Given that we see this shared mathematical language, could the power of abstract structures, like the inner product, hint at some universal principles? Principles for how any complex system, natural or artificial, ends up organizing and processing information.
Like, is there something fundamental about this mathematical operation itself that makes it so useful for modeling complexity, whether it's reality or meaning?
Exactly. What deeper insights might that offer about reality and meaning themselves?
Yeah.
Something to chew on.